here and paying attention. So class,
Yes.
got one yes. Vincent, do I get a yes? Can I get a whoop whoop?
No.
No. Okay. Christian, how you doing? You good? No. Your stomach hurts. From what? Did you not eat breakfast?
No, I pancake.
Pancake. School pancake? Just random pancake you found on the ground, walking to school. Kind of like it was like a Nintendo game where you just walk, pick up food, and get a power up.
Oh yeah, Chris, you're done.
All right, so one of my favorite units because it is the math behind a zombie apocalypse. As long as you don't have earbuds in and are staring at your phone, you might actually get something out of this, but not implying that anyone here would do anything like that. So, a couple things when we actually start with zombie apocalypse. So we have a couple different types of zombies. We have the runners. Then we also have like the slow moving zombies.
Like traditional Walking Dead, and then we're talking like
The runners like World War Z.
like World War Z.
World War Z is the runners, and then the traditional is like the Walking Dead.
Realistically, if we get the runners, I think we're all gonna kill ourselves.
Are we? Well, and we're not doing a third, just a two.
What would be the other? What would be a third type of zombie?
Loaders.
Like the like crawlers.
Loaders.
Like the kind from the kind from Left 4 Dead.
No.
The floaters?
Think about State of Decay, Juggernauts, or Screamers.
Where it's an infection.
Well, but I think it's about the speed.
I know, but we're talking about though. We're talking about the math to go behind it though.
Yeah, like okay.
Yeah, so
The-
we can measure the speed of a really like extra slow zombie, like when they're
Yes, then we're talking about the outbreak.
I've always liked
That's what we're talking about here. The differences in the outbreaks. We have The Walking Dead versus World War Z.
I'll survive with Walking Dead.
Oh, so we're just doing like exponential growth.
We're doing the math behind it. Uninhibited and inhibited growth.
Exactly. The Juggernauts grow a lot.
What's the juggernaut though?
Look up.
No. Just tell me.
It's a big zombie.
From what?
State of Decay.
State of Decay. Is that an actual real person that was infected and then, or was that a biological creation that was created in some type of lab or through some radioactive mishaps?
This thing's big as hell.
Yeah.
Like the
It's
bomb.
big. I just know there's a lot of them. There's multiple, so.
Okay, but we're talking about in all actuality how one person is changed from a regular person into a zombie.
But you
Okay.
do it like with the
Last of Us.
radiation turning people into ghouls and all that.
Okay, but that would be different.
But that's the speed of radiation, and I'm pretty. Isn't radiation? Doesn't it disperse?
Do you know that your
Exponentially?
body in itself is already radioactive?
Yeah.
And we need that radioactivity to live. Our cells require it.
Yeah, but everything in moderation.
Yep. Just like pizza. Alright, so differential equation involving inhibited growth and decay. So, rate of change. Remember that? dA dt. The change of A over change of time, right? Okay. Where K is a real number that's not zero. Okay, that's what we're going to end up with. With K is greater than zero, okay, then we're going to have a growth model. And if K is less than zero, it's going to be a decay model. Whenever we're actually starting this off, we have to start with initial conditions and boundaries. Initial condition always gives me with the t equals 0 with time and an a sub naught, which is my initial amount. Okay, so bam, here's the math, the separation of variables here. To actually go from the rate of change, we do integration of both sides for this, and then eventually come down. This is what we're going to do next unit, separating variables, but it's going to come down to this. This is the math behind growth and decay. A is equal to A sub naught, which is my initial condition, times e to the kt, where k is the rate, right? And t is how much time that we're going to have. Okay, here is right here. So growth or decay. So now decay is going to go down to 0. It's approaching 0 over here, where growth is here. Now, these are uninhibited. Uninhibited. So that means it's just going to go on forever here. But there always is some inhibited. Can I decay below 0? So my decay actually has a floor. All right. Assume that a colony of bacteria grows at a rate proportional to the number of bacteria present. If the number of bacteria doubles in 5 hours, how long will it take for the number of bacteria to triple? Okay. So we now know a rate on this one, that it's going to double in 5 hours. So I know that A is equal to A sub naught E K T. So the first thing we're always going to find is we're going to find what it is, my rate. I could use my initial condition that they give me to find my rate. So I know that whatever my initial amount, how much is going to be there in 5 hours? Double. So it would be 2A sub naught is equal to A sub naught E K times, in how long? 5 hours. There we go. Let's do a little math. Divide both sides by A sub naught. I should get 2 is equal to E to the 5K. Algebra-wise, how do I get rid of that E? How do I undo an E? I get ln. ln both sides, so it's ln of 2 is equal to 5K. Divide by 5. K is equal to ln 2 divided by 5. I'm going to leave it like that because you really want to save all your rounding into the very end. So that is an exact answer. Okay, that is going to be an exact answer there. So now I have a K value. Can I plug that in? Because I want to know when it's going to triple. Now, rewriting this problem to solve for the triple is going to be usually the hardest part. Where am I going to say that this is going to triple at? Right over here, right? Same way, this was double, right? Double my initial amount. Does it matter if I don't know what the initial amount is? No. So I know it's going to be 3 times as much as that. So I could actually come through and say 3A sub naught is equal to A sub naught E. Do I know the K? Yes, I now know the K. I'm going to leave it as K because I like using this as an exact answer. And T. We're looking for when. How long will it take for it to triple? So that means that T is going to be my variable here. Do the same little bit of math. Divide both sides by A sub naught. I should get 3 is equal to EK times T. ln both sides. ln 3 is equal to K times T. And to get T by itself, I'm going to divide everything by K, right? So that's going to give me my T. And since I don't know all my ln's by heart, I know that if it is less than 1, but before 0, those are negatives. LNs are negative. And if it is 1 or more than 1, those would be positives. That's about it. That's just from the graph. Anyway, so control, divide, I'm going to have ln of, what was on top? 3. Control, divide again. This is ln 2.
2, yeah.
Yeah. Over 5. Okay. Now, on your calculator, you hit Control, Enter. So that's going to give me about how long?
Oh, wait, 8 hours?
About 8 hours, right? About 8 hours for it to triple. Are you okay, Christian?
About 8 hours for it to triple.
Can you really quick redo, like backpedal one step how you got from the ln 3 over k to the 8 hours?
Okay, what's K?
ln 2 over 5.
Okay. Are you okay with this right here? My top part up here. Are you okay with that?
Yeah.
You're okay with ln 3 equals k times t, right? So I divided both sides by k. So I could rewrite this. Let me make this a little bit better. So it's ln of 3 divided by ln. This is my k, right? That's where I get that. Because this is my k. That's a k. So it's ln 3 over k. And we just plug k, what was in there for k.
What?
Do you know what k is?
No.
Yes, we do. K is over here.
Well, yes, but like literally like show me you getting it to 8, please.
The calculator.
Yeah.
Oh, on the
Like,
calculator?
that's the part like I didn't see. Oh.
You need to
Okay.
take control enter.
Thought you did some fancy shit, but never mind.
Okay, I'm just making sure. I'm worried.
No, yeah, I got it. I
Oh.
just wasn't sure if I like missed a crucial step or something.
No, just plug in the calculator. Sometimes I think I have a stroke and I like, what the hell? All of a sudden there's like all this other stuff going on and I miss it all. Alright, 8 hours. Alright, radioactive substance, rate of decay. Half-life. Half-life is when we get a certain amount of time and we can calculate how many years there will be exactly half of it. That's important. It's half of what the initial amount. When we're talking about radioactivity, if it has a half-life of 1,000 years, it takes 1,000 years for it to decay so far that there's only half of it left. We still have a lot longer for the rest of the half because it slows down at that point. Skull of an animal found in archaeological dig contains 20% of the original amount, carbon-14. If the half-life of carbon-14 is 5,730 years, how long ago did the animal die? It did. Alright, formula. We have right? Now, half-life, this should be the key. In 5,730 years, how much is left? What are you going to get over here for this answer? 1/2 of a sub 9. both sides by a sub naught, I get 1/2 is equal to E K 5 ln both sides. But yeah, let's do ln. ln 1/2 equals K 5730. And now, this is important because this is a ln rule. If there's a fraction in that ln, can I break that apart? Yes, I can. I can break it apart. That's one of the rules. If it's divided by inside that ln, it's the same as the log rule. That turns into what? It's a minus sign, right? So this turns into ln of 1 minus ln of 2. But what is ln1 if you're not playing on your phone? What is ln1? It's 0, right? So this part could just go away. So the ln1 is just going to go away. So this is going to happen a lot in a lot of the problems that we're going to have. So when you see that, just turn into a negative ln2 or negative, whatever the ln is. Okay, that's how it comes out. So this is negative ln2 divided by 5730 is equal to my K. Question? Good? Alright, so now we know the K. Now let's plug in my conditions that I now know that I'm trying to solve for the time, right? We know that we have how much left? 20% of what? The original amount, which is my a sub naught, right? So 20% of that. Can I write that as a fraction? I like fractions. Fractions are your friend, not food. That's, what is that, 0.5? No, wait. 1 over 5, right? Okay. 1 over 5 of a sub naught is equal to a sub naught E K, which is known, times T. K is over here. I'm not going to approximate this until the very end, until I throw it into that last part. Divide everything by a sub naught, I should get 1/5 equals E K T ln both sides. Now, I'm going to skip a step here. If I ln both sides, this is going to become ln what? So it's negative ln of 5 is equal to KT. And then divide by K.
Is that a 5?
That one, that 5 right there, or that 5 right there? Or maybe that 5. I have a bad habit. I'm not picking up my pen enough that it's not reading it anymore. Alright, so now is the time to put it in the calculator? Yes, it is. Alright. Looking at this problem right now, how do I know that this is a decay? That negative ln, right? That negative ln 5 is going to tell me, oh, hey, yeah, there is, it went down. So, let's see. So, we have control divide. We have negative ln of 5. Control divide. No. Negative ln2. Okay. Over.
Or 730.
Like that. And so now I hit Control Enter. There you go. So how old is that approximately? About 13,300 years, right? And it's time for some zombie problems. Uninhibited growth or decay grows without bounds or decays to 0. Okay, that's important because it still counts. Decay, there is a bound, it goes to 0, but you have to know that's not going to just keep going down forever. It has a 0. So that's the bounds on uninhibited. Okay, so we actually have a maximum and a minimum for this one right here. These are inhibited. Now, zombie population here. What would inhibit the growth of the zombie population? Huh? No more humans, right? Okay, so now, so there's a maximum, isn't there? That's about 9 billion. Huh? Globally.
And they find out it was 12 billion.
Yeah.
Didn't they find out it was 12 billion?
Oh, I.
Yeah, there was like apparently like billions of people accounted for.
Oh wow.
So that's like awful news.
Oh. Okay.
Some people.
Oh, is it awful?
Well, the population is also it has a limit.
You're gonna die soon.
Okay. So, are you starving because of it?
Not yet.
Okay. Can you grow your own food?
For now.
Why wouldn't you be able? Can you not? Do you not have access to? Oh, you live in the city.
Yeah.
So, access to clean drinking water and grow your own food. Self-sufficiency is what is inhibiting a lot of people's growth. They live in a city, they don't do anything to produce those products. We're closing down all the farms. Look at the west side of Phoenix. That used to be all farms, all through Buckeye. Now it's all, they paved paradise and put up a parking lot. I can't even remember who sang that song for that one. But still, we're converting the farms into housing. So what are we taking away? We're reducing the food supply to increase the population supply. So yeah, we're stabbing each other for this. Okay, just people need to learn how to be more self-sufficient because they can't count on food being delivered to them all the time just on your app. So, population, there is a limit. What'd you say, 12 billion? Okay, so there could be, and so as it's going to inhibit, is it going to rocket up to 12 billion then drop to 0? And then stop right there? Even if it's the World War Z zombies, is it going to stop right there? Is it just, no? What's going to happen? Is it going to taper off as it's getting closer and closer to that right there, then inhibited? So it's going to curve to there, right? So in this information right here, it actually says that, right here, since the second derivative is going to be less than 0, it will be concave down. So as it is going up, it's going to curve down. So we'll have some concavity as it's approaching my inhibitor. Okay. Now, in that same model, we're growing the population of zombies. But what is decaying at that same thing?
Population.
Yeah, human population, right? Now, is there a limit on what the human population can go to? What would that be? 0. There we go. So we have a limit, but there is also, for whatever reason, we're gonna have those people that, stole all of our money and are living in some mountain somewhere underground as like some Morlocks. And then we have the Eloi, that are gonna feed on them. So that's gonna be us. Anyway, but still, there is gonna be a population that is left over somewhere. Okay. Growth, okay, limiting to amount of zombies, because all the zombies are still gonna try and eventually chase down all those delicious brains. Where Decay, right here, and it's eventually gonna get to a point where there is going to be not enough food for the zombies as it keeps going here, and we got those people living underground. Kinda like the city of Ember. Alright, application Newton's law of cooling, where T is a constant. So, here is the math behind this. I added this to your notes. And the separation of variables. If you notice right here, when we separate variables, C goes on the right hand side, not the left. I don't know why, but it is. When we separate the variables, take an integration on both sides, C is on the right hand side. Because you only have one C value when you put them together. Alright, so down here, this is what we're going to use. U of T, okay, is equal to U sub naught, which is my temperature of the item. So my initial temperature of the item. T is the ambient temperature. K is the rate of decay as it cools. T is the time, and capital T again is ambient temperature. It looks crazy, doesn't it? Okay. Super crazy. So let's go ahead. So my here's formula. Let's plug in. We have some values that we could start off with, because eventually I want to figure out what it is after 20 minutes. But after 10 minutes, I know what the end result is. So I know that my U of T, my temperature, is going to be 60. So I have 60 is equal to, object is heated to 90 degrees Celsius, which is my U of T, or my U sub naught right here. 90 minus my ambient temperature. My ambient temperature of this is going to be 20 degrees Celsius. E, K, my T is going to be how long? 10 minutes, plus my ambient temperature again. So again, we're trying to solve for the rate, which is my K. No. E10K plus 20. Subtract 20 to both sides. I get 40 equals 70 E10K. Divide by 70. I get 40 over 70 is equal to E10K. I'm going to clean up some space. 40 divided by 70 will reduce to 4 over 7, right? Yeah? Alright, and then what would I do to both sides to try and get rid of my E? ln. So I'm going to have ln of 4 over 7 is equal to 10K. So I could come up here and say my K is equal to ln of 4 over 7 divided by 10. And now they give you something else they want you to solve. They want you to solve what? What's the temperature at 20 minutes? So, I'm looking for the temperature, which is whatever my U of 20 is going to be equal to 90, my initial, ambient, times E, K, my time is now 20, plus 20. And the K value, I'm not scrolling through my feed right now, my K value is what we had on that previous one. So we're going to do a little bit of math on this one and then just plug it in the calculator. So, actually I could just plug it on the calculator, right? So, let's see. Parentheses of 90 minus 20 closed E to the 20 times my K. My K was ln of 4 over 7 divided by 10 plus 20. So I'm just having the calculator do everything for me. Just plug it all in. So it's about 42.857 degrees Celsius. Yeah, this problem would really suck if it was like on a non-calculator portion. I would note that right there. All right, questions, concerns, complaints, conspiracy theories. So, yeah, we're done. That's it. So that's why your worksheet's only 1 page long. All right. So that means it's due when? Thursday. Like, share, and subscribe.